Hello, everyone. Welcome back to the AAS YouTube channel. And this is still part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Anders Johansen with us today. Hey, Anders.
Hello.
How are you today?
I am very good, thank you.
What is your geolocation?
Well, I'm sitting in Sweden, in Lund. It is 6 o'clock in the evening. It is very dark because the sun set 2 hours ago. And I'm working from home.
Yes.
Other people are probably also.
Yes.
Mhm.
Sunset at 6. So do you get to see any aurora while you're up there?
No, we're too far south.
Too far south.
Remember, Sweden is the size of California, right? So basically, it's a huge country.
Mhm.
And I'm in the very south, which is closer to Copenhagen than to Stockholm. So we're just half an hour drive from Copenhagen, basically.
Okay.
No
Great.
aurora, just gray. We don't even get snow much anymore because of
Wow.
climate
Yeah.
change. Last year we had no snow any single day.
Wow.
This year we had 1 millimeter of snow
Wow.
one day, and all the kids were out and playing and building snowmen out of 1 millimeter of snow.
Little tiny snowmen. Little tiny.
Yeah, exactly. No, if you're patient enough and you roll long enough, you can build a big snowman also.
Oh, very good, very good. Well, I'm here in Phoenix, and it's 10 a.m. in the morning, in my morning, and it's a blue sky. We'll hit about 20F or so today, 15F, something like that. 15F, 15C. Excuse me, did the conversion wrong there. So it'll be good. So what's the air temperature there in?
It's around freezing. It's just a couple of degrees above freezing. And of course, it would be better if we just drop below and we have some wonderful snow, but instead we just get cold rain.
2 millimeters of snow now.
Yeah, exactly.
Cool.
Mhm.
So Anders, what do you like to do for research?
Well, I like to work on understanding how planets form.
Mm-hmm.
I am a theorist and I work mainly with computer simulations of how you go from dust grains in a protoplanetary disk and up to planetesimals, like asteroids, and then onwards from asteroids to full planetary systems.
Cool.
And I have worked on that ever since my master's project in Copenhagen many years ago. And I continued with as a PhD student in Germany, and I have continued with planet formation ever since I got acquainted with it first. Mm.
Well, of course, these days it's a hot topic.
Yeah,
We are
yeah, it is.
planets all the time now. And
Yeah, it is a hot topic. It's very motivated by exoplanets, I think, which is sort of an explosively hot topic right now.
right?
And I think it also, but also we shouldn't forget the solar system. Like we heard recently
So,
from Hayabusa, the Hayabusa mission to Ryoko brought down samples, and there's a lot of interesting stuff going on in the solar system also.
mhm.
Understanding the Earth, why it's different from Mars, and why Venus is different from the Earth. Maybe there's life on Venus, So there's a lot of things going on in the solar system also.
Well, we could talk about phosphine, but we won't.
No, I will not talk either. I did another podcast or something like this with phosphine, and
We'll leave phosphine alone for right now.
yep,
We'll
exactly.
settle on that one a little bit.
Yeah.
So, speaking of your theory background and what you're working on, this is going to bring us to this really lovely APJ article
Yeah,
on transport,
yeah,
destruction, and growth of pebbles,
yeah.
gas envelope of a protoplanet. And Anders, take us away.
Well, I can talk a lot about this paper. I guess all scientists can talk a lot about their paper. So please break
Good.
in at any time. It's an exciting paper for me because Åke Nordlund is someone that I have looked up to for a long time. He was actually my master's thesis supervisor. He was one of the three, and I didn't work so much with him back then. And we didn't have a paper together, but this is actually the first paper that we have together.
Great.
Åke is an expert on star formation, on a lot of things, but including star formation, and he's very knowledgeable about convection
Yes.
in stars and also in planets now. So he has a new code called the dispatch code. And the dispatch is sort of an adaptive mesh refinement code with variable time step and very modern. And he spent a long time developing this. And this paper is not about dispatch, but it was inspired by a previous paper he did with a student called Andreas Popovas where they for the first time simulated a planet growing and then an envelope of gas around, and actually they could resolve the convective motion
Oh, nice.
of the gas. So as this protoplanet is getting heated by the immense heat from the pebbles that are accreted, and then it has to get rid of the heat, and it does so by convection. And it turned out that there were huge convection cells coming out. So that's sort of what we wanted to attack here. We wanted to understand what happens as you have a protoplanet growing. It's accreting pebbles that are coming in, and that will heat it a lot, and then you have the convective motion. But then the question is, what is the convective motion's back reaction onto the pebbles?
Right.
How do they react to this convection? And they had sort of done that already in a way in the hydrodynamic simulations, but for constant particle size, which you can easily implement into a hydrodynamic 3D code. But if you want the particle size to evolve by fragmentation and sticking and so on, then it starts to get hard.
Right.
So then here we did the sort of opposite approach in a way. Rather than 3D with constant particle size, you went down to 1D static models of the envelope, but then we could evolve the particle size. So it's a typical trade-off, right?
Right.
Between dimensionality and the depth of the physics, if you wish. So that's what we wanted to do here. I could also highlight my affiliations here. One, Lund Observatory, Lund University. I've been there since 2010. But I'm originally from Copenhagen, and actually just last summer I accepted a job as a professor at the Center for Star and Planet Formation at something called the Globe Institute at the University of Copenhagen. That's a new institute that was founded in 2019, 2018. A very research-oriented institute with an emphasis on understanding the origin of the Earth, the origin of life, the evolution of life. So that I've been now double affiliated for 6 months, working in 2 different places, and within the next 1 or 2 years, I have to transition 100% to the University of Copenhagen, or I have the right to come back to Lund also. So there will be sort of a transition period now. But this is one of my first papers with the Globe affiliation also.
Congratulations on that new position.
Thank you very much. It's exciting to be in 2 places at the same time. It's very easy to make a double work, single salary double work. So one has to make some pretty harsh choices sometimes, particularly in these Zoom days where you can participate in all meetings, no matter where you are, right?
Yeah. It's one
So
of the
that's the way.
travel.
Yeah.
Losing.
All right. So I guess we talked a little bit before about how to present the paper, and I think maybe we take it figure by figure. That's how I normally read papers anyway when other people write papers.
All right. So let's go to figure 1. All yours.
Thank you. So I can see it scrolling slowly here. There we are.
Bandwidth. Okay.
Yeah, no, it's fine. I can see it. Okay, so there will be a lot of these figures here. It's sort of one of these papers that evolved as me playing around with IDL to do some stuff, and then eventually it became a paper. But then also a lot of the figures have sort of a similar feel to them. It's also because it's a 1D. I can't show any nice 3D stuff here. It's all these 1D measurements here. Okay, but anyway, the question is the following. We have a protoplanet. It's growing. It's growing by a mechanism called pebble accretion, which I've worked a lot on, which basically means it doesn't grow by accreting other protoplanets. It grows by accreting tiny pebbles that are sitting in the protoplanetary disk. These pebbles are observed around young stars. There are many pebbles there, and they can be accreted very efficiently. And the main thing that makes pebble accretion efficient is friction between the pebbles and the gas. So again, my hand is a protoplanet again, and I take a planetesimal or another protoplanet, and I move towards this protoplanet. And what happens is that I will get scattered, right?
Yep.
I'll change my direction, but it's very unlikely that I will actually become accreted, even with an increased cross section because of the gravity. Most of my interactions end in a simple scattering.
Yep.
So I replace the planetesimal here by a small pebble instead. Sort of follows the same trajectory, but then it loses energy because of friction with the gas, and then it spirals in, and it is accreted by the protoplanet. So that's a mechanism that we and others proposed maybe a decade ago now, and it looks that it can explain a lot of properties about planets. But then there was a paper coming out also in APJ by Ali Deep and Thompson, who were basically finding that as the pebbles come into the envelope, the pebbles would get destroyed by the high-speed collisions there. And then they said that it means that the pebbles will not be accreted at all. You just form a lot of dust that would just be thrown out of the envelope again.
Mm.
And that's sort of what we wanted to explore here, whether it is really the case. And the main thing we wanted to explore here is, again, convection, but convection not as a diffusive small-scale process, because that's not going to lead to throwing out dust, but for convection more consisting of enormous large-scale convection modes that come out with the hot gas, and then the cold gas sinks in these small thin lines. And this means that convection can be more transporting rather than diffusing. It's because it's so large scale. Let's come back to that basically. But here we have some models that we did for the protoplanets envelopes. So it's the gas density on the y-axis in SI units, which I like a lot. That's a function of the distance from the protoplanet basically on the x-axis there. Exactly. It's in units of the hill radius.
Yeah. Mm-hmm. Okay.
Yeah. So that's why 1 is sort of where it becomes the disk. And then depending on the mass, no, not on the mass, depending on the distance from the star, the surface sits at different places. So this is sort of the nomenclature or the style that I use here, is that there are 4 colors. Let's see if I even remember here. Yeah. So yellow is 1 AU.
Yep.
Exactly. Orange is 3 AU. Red is 10 AU, and blue is 30 AU. And then 4 different masses of the protoplanet. 0.1 is the thin one, 0.3 is the medium one, 0.1 is the thicker one, and 3 is the thickest one. And it's sort of a natural color scale with the hot colors close to the star, and a natural mass scale also with the thickness of the line. So I hope the readers can appreciate that this kind of style makes sense, so I don't have to show this legend all the time. Yeah. And there you basically see the envelopes as they look. It's calculated from 1D kind of stellar methods known from stellar structure. I guess that's something you would know far more about than me, probably. Stellar structure.
I don't know. Who knows what I know?
Yeah, who knows what you do? Yeah, okay. Anyone would know more about it than I do. This is just simple 1D equilibrium models, basically. And what you see here is the density in the protoplanetary disk. You see at the outer edge, if you go to the 10 to 0 on the x-axis, and then you go up, you can see that when you're close to the star, you get a high density. And when you're further away from the star, you get a low density. And then you see the density increasing as we go towards the surface of the protoplanet, basically because there's gravity and there's a hydrostatic equilibrium. Yeah.
Yes.
Yeah, that makes sense.
Mm-hmm.
And in figure 1b, we see the temperatures also, how much they actually rise. So they are going up a lot, basically, up to thousands of Kelvin when you come close to the protoplanet. You see that it's mainly convective, so the adiabatic regions are marked with a thin line on top here.
Mm-hmm.
Basically, the luminosity is so high that it's basically convective everywhere, except in tiny regions around 2000 Kelvin. You see a little squiggle, a little, yeah, exactly there.
Right.
This seems to be, it's a transition in the opacity law that we used. It's probably, it's the vanishing of the silicate dust. 1000 Kelvin, that means that the opacity starts to drop with temperature.
Sure.
And that tends to be stable towards convection if the opacity drops with temperature. Normally you want the opacity to increase with temperature. That will normally trigger convection, but here you get a little radiative zone there. Yeah. All right, so far so good. I still remember the paper.
How do you determine when do you have the physics in there for when a pebble is destroyed and when it is created?
Yeah. We added a lot of that later, actually. Yeah.
Okay.
Do you want to do it a bit non-linearly? We can go over to that immediately. Then we have to skip to one of the later figures, but yeah. No, the point is we want to. This is not particularly interesting figure 1, but we want to put dust into that and see how the dust evolves, basically, right?
Got it.
So we can see what happens now if we move on to the figures, and we can also skip a few figures, I guess. So we don't have to go through all of them.
Okay.
Now it gets sort of getting to be there, right, with this figure here. So now we're adding something I would say new. This is the terminal velocity of a millimeter-sized pebble for the same models.
Okay.
And we see the terminal velocity in meters per second. And we see sort of the same trend for all of them. The terminal velocity starts low. So when the pebbles come in, they're falling slowly. Then it goes up with distance. So if you go out to where it says 10 to 0, you see that it goes up. So the gravity starts to become stronger and stronger and stronger.
Okay.
And then at some point, the terminal velocity starts to go down. That's because the density of the gas becomes so high, basically, that it slows down these particles as they're coming in. First, they're accelerated, and then they're encountering the really dense gas, and then they're slowed down. And then there's a little wiggle in the end, which is something that goes up again, which is something with the transition in the drag law regime that's not particularly important. So we get many scales here. We get something from 1 meters per second, which is low.
Yeah.
And almost in the sticking regime, and up to a kilometer per second, which is terrible if you are that's not terrible if you're a little igneous pebble from the beach. They can probably survive that. But remember, these pebbles are dust aggregates. So they're basically millimeter-sized pebbles made out of micrometer-sized dust. It's a bit like the consolidated sand you can take up from a sandbox after the rain. If you make sand wet and then dry it,
Yeah.
you can sort of lift these patches of coherent sand, but you also know that a little bit of it's gone basically, right? So a kilometer per second is certainly bad. But the question is, of course, that's something that we discuss a lot in the paper. Is one thing is you can identify speed and say this is too high. The pebbles there are going to collide and destroy each other. But the question is still, is it optically thick or optically thin to collisions? So maybe there's simply not enough space to collide over, because at some point you're going to hit the surface. And even if you're moving a kilometer per second, you still got to find a collision partner before you get destroyed. That's part of it, which we will see in some of the later figures here.
Cool.
If you go to figure 3, I guess. Okay, what is this?
Density versus radius.
Yeah, wow. Okay. Yeah, it looks so complicated now. I hope there's no bug in the code anyway. I mean, when you look at it, you gotta get worried as a theorist that 2,000 lines of IDL code. Yeah. Okay, but it makes sense. I did check, of course. But this is basically telling you the dust to gas ratio, just based on the speed of the pebbles. The slower they are, the more they pile up. The faster they are, the more they anti-pile up, so to say. So you sort of get anywhere in this envelope that the dust to gas ratio is not that high. It's not between 1%.
Yep.
And 10%.
Yeah.
It's not incredibly high, at least. That's because everything's just falling down, right? So there's pebbles coming in, they're moving. When they're moving faster, they get a lower dust to gas ratio. When they're slowing down, they get a higher dust to gas ratio, and eventually they're going to hit the surface of the protoplanet.
Yep.
And that brings us to figure 4, which is basically what is the length scale to collide with another pebble of the same size?
Good.
Divided by the distance you have. Yeah, so it's sort of the optical depth, or the inverse optical depth, I guess. So high value means no collision. Below 1 means collisional. High above 1 means not collisional. And it's sort of interesting that a lot of the like the blue lines there, where there was very high speed, kilometers per second, fine, but also the pebbles don't meet each other really, so it doesn't matter too much.
Yeah.
There's a kilometer per second. I think if you just move on to the next figure, I can tell that story better. There will be better figures.
Oh. Okay.
Yeah, here, Victor. Yeah, you said it was okay with interruptions. Hi, Victor. Okay. Yeah, it's my 4-year-old Victor who is coming to say hi. Jeg kommer ned senere, så skal jeg have den. Okay, and he gave me something to drink.
Hi there. What's his name?
Victor with a K.
Victor. Hey, Victor.
Yeah, and he left again. Yeah.
Okay. Maybe he wants to come in and talk about this figure.
Yeah. No, he doesn't understand this. He likes math. He doesn't appreciate astronomy yet. he keeps on claiming Mars is a star. I had a lot of discussions with him. Someone at the preschool told him Mars was a red star, and I said, no, it's a red planet. He says, no, it's a red star. Minutes later, we were both crying, more or less.
Cool.
Okay, very good. Then, before we go on with actually evolving the particle size distribution, we made use of something that's been developed in planet formation in the last decade, which are simplifications to the particle size in equilibrium. So there is one model that's been developed a lot around Case Dullemont and Till Bienstiel and others in Heidelberg and Munich.
Yes.
Which is that one can calculate the size that you will become, given you know the collision speeds. You can again.
Hey there.
Så vil du sige hej?
Hi.
Korn om er der i kaffemaskinen?
Nej.
Okay, Victor, jeg har lidt møde, okay?
Ja.
Okay, okay, there was corn in the coffee machine. That's not the common way to make coffee, but apparently possible. Yeah.
Cool.
All right. Yeah. Okay, so this gives you basically that the larger the particles are, the faster they collide. Hence, the other way around, if you know how fast they collide when they fragment each other, then you know the size. Pretty easy to calculate, and you can actually then calculate it here, sort of. Interesting that the particles will go down in size first,
Yeah.
per micron, and then as the collision speeds become lower, they will go up in size again. It's also telling you this bit on physical, that you just put the size to the limiting size. But without any physics in it, of course, it's unrealistic that it should go down to a micron and then up again. We don't have any modeling of the actual growth here, so this is just sort of a...
Yes.
Yeah. So if you go to the next figure, we can continue the story.
There you go.
There we are. What does this show? Yeah,
Convective speed.
Speed, yeah. So this is some mixing length model we used for the convective speed.
Okay.
It turns out that convection cells are huge and they are fast. So between 100 and 1,000 meters per second. That's way faster than the terminal velocity that's in figure 6b. Convective speed on the x-axis, terminal velocity of the particles on the y-axis.
Yeah.
The convective speed is higher than terminal velocity, means that the particles don't really care about the sedimentation. They care about the big convection cells.
Right.
Will be brought up and they will be brought down again.
Okay.
If you go down one, then we are now in the models that include the convection. So now we include the convection speed in the dust to gas ratio, and we are still landing around 1%, 10%, 0.1%, not so high. And then we can also calculate in figure 8, we can calculate the relative speed of collisions from convection. And this is not normally done. Normally in planet formation, we like to calculate the relative speed from Komogoro turbulence. Then we know what the speed is from the particle sizes. Then you need to know something about the integral scales of motion, the turnover time scales, and so on. And similar, I think, to what they did in Ali Deep and Thompson, the paper that was doing something similar. We calculated a collision speed also here from convection using the tools from planet formation. And it becomes something like the square root of the particle size or something, I think. And you see that you get here really high collision speeds again. The 1 meters per second is marked here. That's got a typical threshold for fragmentation. Yeah. And you can see the speeds here are really, really high, dangerously high. Yeah, if we go to figure 9, we can have the story unfold.
Stack. So let me go there.
Okay. Oh, there's this one, yeah. So here's again the calculation of the fragmentation speed, of the fragmentation size, for the models with convection only, and below the ones that have convection and sedimentation. And you see that the convective collision speeds are enormous. There's also an issue with the convection. See if I can explain the following way, that the sedimentation speed is linear with the particle size. The particles are too fast, they will collide, and if they are 10 times smaller, they collide 10 times more slowly. So it's easy to become a smaller size that survives. Convection speeds, the collision speed goes at the square root of the particle size. meaning if you want to slow down by a factor 10, you have to become 100 times smaller. And that's why it really did destructive collisions. You, in the outer regions of the Hill radius, you get everything monomerized down to 1 micron. But then again, the increase again as we come closer to the protoplanet surface, because the speeds there are much slower. But again, it has no growth physics in it, so it's just sort of it's just a calculation of what we think might happen, but what we still got to do the actual solving the Pebble sizes evolution that we have here at the beginning of chapter 5.
Right.
So if we go to figure 10.
Okay.
It's slowly getting, yeah, exactly. See if I remember what this plot is about. This is actually something where I read a lot of papers about dust collision experiments, and I wanted to find out what happens when dust grains collide at different speeds, and particularly something not only that, imagine a small dust grain hits a pebble, and the pebble will break up. There will not be any sticking. The question is, how much mass does it take off? Does it take off only its own mass, or more mass, or a tenth of its own mass? So sort of the erosion efficiency, that's sort of what this effector is. The effector tells you as a function of, so we have a target, we have a projectile, and the effector is the amount of mass that the projectile takes as a function of its own mass, so to say. So it can be 1, then a projectile comes in, it makes a little crater, and it excavates the same mass as its own mass. Or it can be 10, or it can be 100. It can be very, very high. So you see these lines here. That's a function of the projectile mass, basically. That the small grains, the micron grains, are the ones that excavate most relative to their own mass. Some of them at 300 meters per second, they can excavate 100 times their own mass.
Yeah.
And it starts to go down, actually. So as we go more and more to larger and larger grains, then more and more of the kinetic energy is dissipated in the impactor and not in the projectile. So then there's actually less and less efficient erosion. And then it changes when the red lines go down. It changes from being erosion to being sticking, and then they're replaced by the blue lines. So then you can actually have this kind of snowball effect where it's like throwing a snowball at a wall. Most of it will fall down, but some of it will stay behind. That's the blue line that's showing mass growth, not particularly efficient, but some mass growth happening. And we can see the speeds there happening at speeds up to 30 meters per second. So these are actual experiments people have done, and we sort of, I hope this figure will be useful for others, because we sort of compiled a lot of experimental data into it by groups in Braunschweig and groups in Münster in Germany who work on experiments of dust collisions.
What's going on at around projectile sizes of 2e to the -4? All of a sudden you get a change in the behavior. Everything's
a change in the behavior. That's between that the mass ratio is large, then you get one collision regime, and the other one is when the mass ratio is not so large, when it's similar sized particles.
okay.
Then you get some different experiments that are showing more sort of fragmentation. It's not erosion anymore. It's more sort of pulverization, fragmentation. And then things start to be bad. You see there's no blue, nothing can grow anymore.
Right.
And you see particularly this factor 5 in between the projectile and the target and the projectile. That's the 0.2. No, that's where the red lines start to go up. That's when you can have really dangerous destruction. So these are some of the most dangerous collisions that you can possibly have.
Okay.
Yeah. Mm-hmm.
I'm with you.
Yeah, very good. Then we can move on to the next figure.
Very cool. And boom.
Oh my, yeah. Okay. These are now models that include fragmentation, sticking between particles. And I basically take millimeter-sized particles and I rain them down into the envelope, and then on the way down, I evolve their size distribution.
Yes.
And there we see what I said before, that, yeah, we do have very destructive particle collisions, but they don't happen so often. we don't get these kilometer per second collisions very often because the collision length scale is so enormous. So in this case here on the these are two different models. One, the issue with this, what is not so consistent here, is that I'm following a pebble coming down, but I need to know the density of the pebbles in the environment. So I need to sort of know collectively what happens to all the other pebbles.
Right.
And I need to do some assumptions here because it's not a real correlation model. It's just following a single one. So then in the one case, I say that the fragment density is the same as the pebble density. So there are the same amount of density in the pebbles coming down as the fragments that are formed.
Okay.
In the right case, I say there's a fragment flux, the same as the pebble flux. And the right one is a little bit more dangerous because then it's not the density that's the same of the fragments and the pebbles, because there's this sort of back reaction where the fragments produce more fragmentation, produce more fragments, produce more fragmentation. That was the key thing in Ali Deep and Thompson, which was the paper that we were criticizing or addressing here. And here in the right plot, we're basically saying, oh well, actually maybe the fragment can build up to a mass where the flux is the same as the pebble flux, meaning that when the fragments are small, if they say the fragments were 10 times smaller than the pebbles, then they would have to be 10 times more in mass to have the same flux. So because the fragments fall more slowly, in this case here, then also there will be more of them. And there you can see you get, particularly the blue ones, that's 130 AU, you get very much destruction on the way, but then you get a build-up in the end. And this is now physical, that the particles do stick and collide to larger sizes as they come closer to the surface of the protoplanet.
Mm-hmm.
So a small size, and then you get the big size again.
Huh. Interesting.
Yeah. Okay, so we can move on to figure 12.
Okay.
Which I think we are starting to be at the end of the figures. Yeah. Now these are the ones that include the convective gas speed. And the convective gas speed has two effects. One, the collision speeds are much, much higher.
Yeah.
Or three. Two, it's harder to get out of the collision speeds because of the square root of the particle size effect. So when you get smaller, you have to get really small to not fragment. But then there's a positive effect, and that is that the particles are now not sedimenting with the sedimentation speed, but with the speed of the cold downwelling gas. So the gas comes up from the surface of the protoplanet hot, and then cold filaments move down, and they move down with a kilometer per second, meaning that the pebbles have less time to collide because they just take sort of a highway, a super fast train down to the surface of the protoplanet. And there you can see sort of a bifurcation in the results here when we're close to the star. So the yellow and the orange and the red, not much happens.
Right.
At least for the smaller protoplanets, it's worse because the gas density is less and therefore the pebbles not slowed down. And then when you go out far away from the star, again, it's the same effect. When the gas density becomes low, then the pebbles are not slowed down so much on the way in, and then they can actually collide at relatively high speeds.
That's right.
So you get this kind of result, a bit surprisingly in a way that when you're close to the star, where the Keplerian speed is high and all speed should be higher, but then the gas density is so high that the pebbles really don't have much collisions going on, and the convective motion sort of shooting them down to the surface of the protoplanet. And when you go further away from the star, it starts to be more problematic because the gas density is so low and so on. So that's sort of what we're seeing with the blue. And that's sort of what we put in the abstract also. I like, in a way, if I really have a caveat in a result, not to hide it away, but to put it in the abstract so that people can address it or I can address it later. So we actually put into the abstract that there are still some issues. We said pebbles do survive because we think Ali Deep and Thompson did a similar analysis, and they concluded that the pebbles are all fragmented down to dust, and then the dust is diffused out. We said no. If you use a more physically realistic model of convection, then convection is not just diffusion, but it's also kind of large-scale transport. Would actually help you. You could take the fast lane all the way down to the surface. But out of the outer 30 AU, for the millimeter-sized pebbles, it does start to look a little bit bad. So maybe the pebbles wouldn't have to be 100 microns there instead or something. That would be a solution.
Okay.
So I think that's sort of it. I hope it makes sense. And there are some papers in the appendix. We don't have to go through them particularly.
Cool. Let's go back to that abstract you mentioned. Yep. There we go.
Yeah. So we say in the end there, the sizes are amenable to accretion at the base of the convection flow. Small protoplanets from far from the star nevertheless erode their pebbles to sizes below 10 microns. Future hydrodynamical simulation will be needed to determine whether such small fragments can detach from the convection flow and become accreted by the planet. And by detach, I mean you come down with a cold downwelling flow, and then the question is, can you then accrete onto the surface of the planet, or will you catch right up again because you're so small that you're just moving with the gas? And I think that this means we need more hydro simulations now.
So let's go down that route, since that's sort of the future, the next steps.
Yeah.
So what are some of the next steps in this as you look, let's say, over the next 5 years or so? Are there aspects of the physics here that you could do in 2D? Although we all understand 2D has its issues.
Yeah, I think actually 2D has issues. I think 3D will be the way forward.
Sure.
So I mentioned in the beginning this dispatch code that Åke Nordlund and others have developed, and it has particles in it. It has adaptive mesh refinement. So as you go on close to the planet, the mesh becomes finer and finer, and the particles are resampled in clever ways and so on. And right now, it's all about getting the particles to interact. And it is possible actually with the stuff that I found for this paper, we can directly take some of these methods and go directly into a hydrocode, and then we can evolve it. So I have myself worked a lot on particle interaction models in 3D hydrocodes. So basically, what I like to do is to have superparticles. You have one grid cell, just do it in 2D here. You have a lot of particles, maybe not a million, but you can have 100 or 1,000, and they're sitting everywhere. And they are not, each of them does not represent one pebble. Each of them represents like a swarm of pebbles. Yeah. So you can't do normal collision tracking as you would do if they were stars, if they were planets. What you do then instead is a statistical collision tracking. You consider each of the superparticles to be a swarm inside of the cell, and then you can calculate the mean free path and the mean collision time. And then you can say, well, if the mean collision time is 10 and your time step is 1, then the probability that a collision happens in this time step is 10%. And if it does happen, then you treat the collision as if they were physical particles. Yeah, they can bounce off each other, they can merge, they can shatter each other. And that's sort of a quite nice way of solving the correlation equation. It gets a bit noisy, of course, but it's very, what's good about using particles, actual particles, to solve the correlation equation is that they naturally resolve the right mass, so to say. Okay. Alternatively, you have to use bins where you say we have an additional dimension in our hydrogen simulation, which is the mass of the particles. And then you have to take bins from a micron up to several millimeters and interact all these bins. And it can be done, but it's not as intuitive, I would say.
Cool. Well, it's well worth doing to resolve some of the questions that you alluded to about the taking the fast lane down on the freeway and what happens as you get close, right? To the circle.
Yeah. Actually, I have a PhD student working with Åke Nordlund and with Troels Haugbølle now also on answer on these questions. Another question is also volatile. So, what if the pebble comes in ice covered? Then it encounters a temperature of around 160 Kelvin at some point where the ice sublimates. And the question is, what happens to the water vapor? Does it stay there? Does it go back to the disk? And this is, of course, important now for water and planets, habitability. Where does Earth water come from, and so on? And I think we can go to hydro simulations, and I think the answer often comes from 3D. It's good to do things in 1D to play around and so on, but going to 3D will certainly give answers that one has less control over. Let's say it that way.
Right. Yeah. Well, 1D can also inform subgrid models.
Right.
Whether it be a subgrid or a superparticle or whatever.
Right. Yeah, you can sort of see this paper as the preparation for that, for a subgrid model. Exactly.
Cool. Very good. Awesome. Well, Anders, I want to thank you so much for spending some time, and your son for spending some time talking about your lovely APJ article. So
Yeah, but thanks for contacting me. It's always fun to talk about your own paper. So
yeah, and it's good for the community to see the actual person who's doing the work. Otherwise, it's just the name on
yeah,
so meet people. So it's pretty cool. All right, everyone. Thank you so much, and we'll see you on the next one. Bye bye.
bye bye.